week on Friday. And this time I won't really have more of an extension of a deadline, since I want to also send you on Friday or Saturday the solutions so you can use them to study for your midterm. Now, midterm is going to be 2 weeks from now. So next week we have classes. The material that we're going to cover in the 13 will not be part of the midterm. So everything until today will be part of the midterm. Thus, our midterm is going to be the 20th. At this point, I haven't fully decided how we're going to do this. I believe there's only one person who's having the midterm, or who's taking the class fully online. Is that true, or were there two people doing that? Who else is taking the class online, only online? So it's not physically in the US or in the BART area. Yes, I remember, Norman, you mentioned that you were. So I think everybody else is in the area. Thus, we're going to, unless I have a change of mind, we're going to be having the exam in person, and I'm going to address, or we're going to figure out something, Norman, so you can also take in the same amount of time, but from home, and see how can you submit that on time. In any case, the exam will be the 20th, so mark that on your calendars. I think next week you don't have anything, since both Ajit and Tom are out of the country. And I believe you have 2 days off next week, so you have the days off. I'm still going to be working, so you can contact me if you have any questions from the homework as well.
Professor, is it gonna be open book, or how will be the structure of the midterm?
Good question. No, will not be open book, but you can have a single sheet of formulas and or tests that you might need. Everything else, basically, you have to study for everything else. So it's not going to be an open book exam.
Will we be using data or?
No. Every question that relies on formulas or questions and on empirical analysis, I will give you the results. You have to either choose which one is the right one and make interpretations of that one, or do something based on the information from the tables that I will be giving you. There will be no data involved in this. So I will be doing all the estimations. You just have to use that and make inference from that. Also, the exam will try to test you on whether or not you understand the concepts behind everything that we're covering. So a lot of the concepts that we have gone into, what is heteroscedasticity, what's normality, what are the consequences of, why do we care about normality, what happens when the linear assumption doesn't hold, etc., etc. All those kind of questions might be part of the exam. Any other question before we start the class? That's true. Next week, we're actually going to have our first class in person. I'll be there, so I hope to see you all there. And it's going to be in the bigger room. So looking forward to see you. Although I'm going to still be streaming the class for Nomad, since he will still be taking it online.
Sorry, when will that be?
Next week. Next week I'm back.
Awesome.
Yes. So looking forward to see you all, guys. Hopefully it will be easier for you to ask me questions in person, or not, in which case it will be easier for me to choose who to ask questions. So be prepared. Remember the question, something that, what was it? Kibius mentioned about your, the quizzes. There's not going to be any quizzes, but because it's going to be in person, I might have more time to actually quiz you in person. So be prepared for that as well. Okie dokie. So what are we going to see today? And let me know if you already see the presentation. What we're going to try to discuss today is basically address some of the violations of the assumptions of the linear regression model. And the first one that we're going to talk about is the problem of heteroscedasticity. Specific, what it is, how to detect it, and what to do about it. So who told me what is the problem of heteroscedasticity?
It's when
Yeah.
I think it's when we have problem with our residuals, when the variance of residuals are not equal, and
Exactly.
if we plot it, it's kind of scatter.
Exactly. So the problem of heteroscedasticity basically means that the residuals have a variance that change or that varies based on characteristics. So it could vary based on other things, but that we don't really care since we hope that the other things are quote unquote homocelastic. So we don't really care, they get fixed. But we care that these errors, or we really wonder if these errors have either a constant variance or the variance increases based on the values of characteristics. So what exactly would this look like? So I have here a couple of examples on what would happen when you have a model with both homoscedasticity and with heteroscedasticity. In the first case, the plot on the top is trying to reflect a situation where y is a function of x, but there is homoscedasticity on the errors. You can see that I plotted a couple of lines just to show you where most of the variations of the errors are going to be. So you can see that except for a few points, almost everything falls within this band. So what happens when you have that? Look at the variation of the slope of the curve. It moves, but it doesn't really move much. It's relatively stable. Now, what happens when you have heteroscedasticity? With heteroscedasticity, it means that the errors or the dispersion of the errors changes based on the values of x. Now, how can it change? It's going to depend a lot on the functional form. But for us, let's assume that the variance changes in such a way that there is very little variation around zero, and that's the example I'm writing here. It could be different. This is just a particular example, but the variation increases either the higher or the lower the values of x are. So what are the consequences in this case? You can see that even though the model is supposed to be the same one as the one on top, there is more variation on the slope. It wiggles much more than the case of homoscedasticity. Now, what happens? What are the implications of this when you actually try to estimate the beta coefficients? Now, what I plotted here is I basically ran what it's called a Monte Carlo simulation, where I did this 1,000 times. I have a model where y is a function. Let's see if I can write it here. I write a very simple model where I say y is a function of 1 plus 0 times x plus an error. So basically, there should be no slope respect to x. I know that for certain. In one case, I assume the model is homoscedastic, and in the other case, I assume the model is heteroscedastic by multiplying this by the absolute value of x. When I assume the model is homoscedastic and I start estimating this 1,000 times, get the estimates, I do find that my results are going to be unbiased because in average, the distribution is really around zero, as I was expecting, because that's how I constructed. And the distribution is, let's call it, is what we expect. So this blue line is the one that we are expecting the distribution of the betas to be. Now, if I introduce a model with heteroscedasticity, and even though it's not so clear here, but I make sure that this error has the same variance as the error without heteroscedasticity, I do find that the distribution of the betas is much wider. So we have the same amount of overall variation of the errors, but because of the presence of heteroscedasticity, the betas now have a wider distribution, which implies what? Implies that every time that I run the model, even though in average is going to be unbiased, when I run a single model, I might be more likely to reject the null hypothesis that the coefficients are equal to 0, because the distribution is much larger than what our simple model would tell us. So just to recall all the assumptions for the linear regression model or for the ordinary least squares. You need to have that the model is linear in parameters, you have random sampling, no perfect collinearity in the sample, that all the variables of the model are completely exogenous, so are not related to the error, and that the variance is homoscedastic. Under these assumptions, your OLS estimations are going to be blue, meaning are going to be the most efficient, meaning the beta coefficients have the smallest variance. So it doesn't matter which other scheme you come up with the estimations of the betas. If you do this exercise 1,000 times, the OLS will have a much tighter distribution of the betas. Now, something that I mentioned last class as well was that if we include assumption number 6 over here, we include assumption number 6 of normality, then the estimations are not only best linear estimations, but are the best unbiased estimations of all. And one of the answers from the PRAS homework, that when you have large samples, the normality assumption is not needed for, at least for statistical inference. For smaller samples, it's required because if you have your errors that are normal, then your betas are going to follow a normal distribution. Then you can use T's, F, etc. If they are not normal and your sample is small, then you cannot really use the standard statistics. Now, what happens when we drop assumption number 5 of homoscedasticity? As I showed you at the beginning, even if my model is heteroscedastic, my coefficients are still unbiased and are going to be also consistent, meaning the more information that I use for my model, the variance of the coefficients is still going to reduce. Even though it's larger because of heterostatic errors, in the long run, that variance will still reduce the larger your sample is. So consistency means asymptotically, when n goes to infinity, the variance of your estimations goes to 0, so you are able to estimate exactly the population parameter. Somebody's made that comment. What about the R-squared? The R-squared doesn't have any changes on the interpretation either. Because you can still interpret it as how much of the total variation of the model is explained and how much is unexplained. That still remains as the correct interpretation of the R-squared. So, what under heteroscedasticity? Your estimations are still unbiased, are still consistent. Your R-squared can still be estimated as usual. So what's the problem? First, under heteroscedasticity, the variance of the OLS are now incorrect. And that, again, you could have seen based on this figure over here. What we estimate as a variance using the formulas that we covered last week or covered in the past kind of tries to estimate the variance of this blue line distribution. But if your model is heteroscedastic, the correct variance should be this red line. So we are going to be, and this is just for this example, we are underestimating the amount of variation of the coefficients. And if we are underestimating the variance of the coefficients, then the variances that we're using are going to be incorrect, which means that the F statistics are going to be incorrect, the T statistics are going to be incorrect, which makes them not valid under heteroscedasticity. So what happens with heteroscedasticity? You cannot run your standard analysis unless you do something about it. Some other consequences are that under heteroscedasticity, OLS is no longer the best unbiased linear estimator. It's not blue anymore, because there are going to be other estimators, and we're going to cover some of them, that will become more efficient than OLS. Thus, what we need to do for any kind of analysis is learn how to detect that there is a problem of heteroscedasticity and what to do to fix that problem, because it is to some extent fixable, and sometimes you might not even need to worry about fixing if the problem is not present there. So this just replicates what I showed you before. How bad could be the problem of heteroscedasticity? So if any of you wants to run this experiment, you could do that. And the basic experiment is as follows. Again, I'm going to do all of these 1,000 times. I create a random sample of x's. I create a variable y that is equal to 1 plus the error of absolute value of x. That way you know that the you know that the variance is going to be heteroscedastic. It increases with the absolute value of x. And I estimate this simple model. So if I do that, and I construct the t-statistics that come from this model, we know, at least we should expect, that about 95% of the values should fall between 2 and -2. That's the rule of 2, or the critical values when you don't want to look into the tables. If it's less than 2, or rather less than 2 in absolute value, we usually say that things are statistically non-significant. If it's higher than 2, they are statistically significant. Now, based on my model and how I construct it, I know that the beta should be 0. So at least 95% of the cases should give you a t-statistic that is less than absolute value of 2. What happens when I do that? And I basically plot all the values. This is the distribution of the t-statistics that I get. And the value of this plus this, so this and this, is much more than just 5%. So the same thing that I showed you before. Because we have heteroscedasticity, we're going to tend to over-reject the null hypothesis of no effect, of that things are significant, because we are overstating the amount of dispersion of the coefficients, and we're not accounting that when we estimate the variance of the beta coefficients. So how do we test it, and why is it a problem? Again, we are going to test for heteroscedasticity because OLS may not be the most efficient estimator anymore. Now, what exactly do we mean efficiency? And this is a concept that you might want to include not only for OLS, but basically for every other type of estimator that you might think about, that you may learn now or might learn in the future. The most efficient estimator is that uses the most information about the data. So you know something more about the data, you can improve the efficiency of your model. That is why we kind of improve a little bit when we go from a model without the normality assumption to one with normality assumption, because adding that additional piece of information technically makes our estimation more efficient, because we're using more information to estimate the standard errors. Now, the reason why OLS is not efficient is because it technically ignores the presence of heteroscedasticity. And we're going to see this later, one way to improve the efficiency of the OLS is reintegrate something about this heteroscedasticity in the estimation, in that way improving the efficiency of the estimators themselves. So first thing first, how do we estimate, or how do you test for heteroscedasticity in the model? So keep in mind that the heteroscedasticity on the model basically means that the variance of the errors, conditional on x, is different from a constant. So this is what we are trying to test. How do we test for this? The first approach is going to be using what is known the branch pattern test. This branch pattern test basically tells you, again, that under the null hypothesis of homoscedasticity, you're expecting that the values of the errors conditional on characteristics is equal to a constant, which implies homoscedasticity. Now, to test for this, I need to have an approximation and figure out how can I test if the variation of the errors changes based on characteristics. What the branch pattern test suggests is that what you could do is simply change this value over here for the sample equivalent. So instead of trying to model whether or not the variance of x is a function of x, you model whether or not the predicted residuals square of the model are a function of characteristics. So at the end of the day, the branch pattern test, what it's trying to tell you is that in order to test for homoscedasticity, you simply need to test if the square of the errors can be explained by the controls in your model. As simple as that. How do you test for that? You can do it in two ways. Both of them rely, depending on exactly the same null hypothesis. That if there is no problem of heteroscedasticity, it means that all these deltas should be equal to 0, which means that in average, the square of the errors does not depend on the values of the x's, which is equivalent to this null hypothesis. Now, how do we test for this? We can use the standard F statistic, or the overall significance of the model, and if we find that none of the variables have a significant impact in this model, then you'll find there is no problem of heteroscedasticity. The alternative is also to use the LM test, which is much better when you have large samples. LM is for large sample, when your sample goes to infinity, so when you have very large samples. For most of the cases, you can still rely on the standard F statistic.
Professor, by rejecting the null hypothesis, it means that we are having a heteroscedastic problem?
Yes, because what does it mean to reject the null hypothesis? It means that at least one of these deltas is different from 0, which means that the variance depends on that value. So the variance of mu depends on x, which means that the variance is different from a constant. That's why rejecting the null hypothesis implies that there is heteroscedasticity in the model.
Okay, got it.
Perfect. Okay, so let's see how do we do this in practice. First of all, a couple of people were mentioning that they were having problems using the Rios command. If you can reinstall it, that would be ideal. So let me actually do that right now, so you can see up here. For my new instance of data.
You had attached a file in the file was didn't run in anything basically. The command seems to work. It was the file
so
using. Yeah.
So that's why what I wanted to ask you now is, when you open your data, install with the last version that you're gonna find from the SSC. I submitted that over the weekend, so you should be able to install Rios from the internet. And to make sure that is the right one, you should have the version 1.1. So you type Rios, version, it should give you the 1.1. If that's the case, then you have the last version, and you can run it using the example I'm going to provide you in a second. So again, how we're going to do the brush pattern test? For this case, we're going to use data on housing prices. Let me copy all of this. That we're going to load it from the web. You can see that everything is loaded here with all the explanations of the variables. We're going to run a very simple model with regression as a function of the lot size, construction of the size, meaning how big the house is, and the number of bedrooms. I could already ask you to make some interpretation of the model, and you would say something like, depending on what is the measurements. Okay, so for example, every 1,000 square feet, the price of the house increases in about $2,000. Every 10 square feet of constructed house with increase in about $1,000, $1,200. And for each additional bedroom, you will have to pay $13,000 more. How do I know it's in $1,000? Because prices is measured in thousands. Now, this model is measured or is estimated under the assumption of homogeneity, and we were just assuming that all these standards are well correct. The question now is, how do we know if we have a problem of heteroscedasticity?
A small question though. It says like the constant is at -21, right? How would you really describe that?
Okay, so that's a good question, and that's one of the things that I asked you in the homework as well. So technically, this means that a house that has no bedrooms, that is constructed, and basically there is no house because the size of the constructed house is 0, and the house of the lot is 0, it would cost you minus $20,000. So the question is, are there any houses that have no bedrooms that is constructed on no land and that is of size 0? So in this case, that is the technical interpretation of the constant, but the empirical interpretation is not really sensible because there are no houses that have 0 in lot size, 0 in square feet, or 0 in bedrooms. Now, you really would like to have a better idea of what is the, let me change it. You want to have a better interpretation of the constant. One of the things that you could do is to recenter all your variables to the averages. Let's say, by the way, probably you're not going to be able to do this because this is a command that I never really posted anywhere, but is to make things slightly easier from my perspective. Lot size minus 10,000. Square feet minus 2,000. Bedrooms minus 4. So right now I'm making a simple regression where my constant represents the value of a house with a lot size of 10,000, a square feet of 2,000, and with 4 bedrooms. Because when that's the case, this is 0, this is 0, this is 0, and that's the only case where this constant makes sense. The 0 in this case is nonsensical. And now to make a small parallelism to the exercise that you had in the homework, the question was to interpret the constant, which makes no sense when you consider somebody with 0 experience, which is possible, but also with 0 years of education, because the minimum years of education in the sample was, if I remember correctly, 5 years of education. So the constant has to be interpreted both in terms of the technicalities, but as well in terms of the data that you have available. Now let's go back to this. So how do we know if we have a problem of heteroscedasticity? One way to do that would be to predict my residuals, and then I could plot my residuals as a function of all the characteristics that I have here, as a function of lot size, to see if it is increasing or not. We have a problem here because we have an outlier, so it's not really clear what's going on. Square respect to square feet. If we take away the outlier, you might say that it's perhaps increasing a little bit with the size of the house. And in terms of the bedroom, here perhaps the most clear that the larger the number of bedrooms, the more variation you're going to see in terms of the residuals. But again, this is just a visual inspection. It's not a formal test. So the formal test suggests you get the residuals, you get the square of the residuals, and then you estimate a simple model where the residuals square is a function of the same variable that you had before. And here you look at the F statistic and the probability, or if you prefer, you just look at the significance of all the variables that you have here. So what do we conclude? According to this, from all the characteristics, lot size has an impact on the square of the errors. So the variance depends on the size of the lot. If I look and I do a joint test, so I could have done test lot size square feet bedrooms, I will also conclude that I reject the null hypothesis that all of these are simultaneously equal to 0, meaning I'm rejecting the null hypothesis of homoscedasticity. And in this particular case, under the assumption of homoscedastic error, I could have just looked at this coefficient, which is exactly the same as the one you have here. So what do we conclude? This model is heteroscedastic according to the Brauch-Pagan test.
Professor, once again, can you show, like, how did you generate the res square in there?
Here you have it on the slides. I first get the residuals of the model. So I have to run first my model, obtain the residuals, generate the residuals square, by just squaring the original residuals, and then run your regression of these residuals square as a function of the characteristics.
Okay, got it.
Okay. So here was the example using the F test, but I also provide example if I would like to use the LM test, which in the end is just a chi-square test. Now, as a side note, probably an LM test is not going to be as appropriate here because our sample is relatively small. Now, what if I use a different model? You remember, one of the reasons why we like to use logs in a model is to reduce the amount of variation on the data and sometimes improve in some of the characteristics of the model. In this case, if I apply logs to all the variables of the model, the log of prices, the log of the lot size, log of the square feet, but I leave bedrooms just as it is, because it doesn't make much sense to add logs to bedrooms as well. I estimate the residuals and I run the same test. I find that this model is no longer, at least that you cannot reject the null hypothesis of homoscedasticity. So a model where the prices, where we estimate the model with directly on prices, the model seems to be heteroscedastic. But if I estimate the model in logs, the model is no longer heteroscedastic. So technically speaking, this model should be better for running statistical tests, because at least the assumption of normality, the assumption of homoscedasticity holds. So I could run direct tests on the coefficients that you have in the model. The interpretation changes. Keep in mind that's the case, that here the coefficients cannot be interpreted the same way that I was interpreting them over here, but the coefficients are more sensitive. At least the standard errors are estimated correctly. Now, as a side note, how do we interpret these coefficients? Because this model is log of prices as a function of log of lot size, this coefficient becomes the elasticity, meaning in how much, if there is a 1% increase in lot size, we should expect to see a 0.168% increase on the price. If there is a 10% increase in lot size, we should expect to see a 1.68% increase in price. If there is a 10% increase in the square feet, there should be a 7% price increase on the house. What about bedrooms? If there is one additional bedroom, we should expect to see a 3.7% increase in the local price. Now, this percentage interpretation for this coefficient, for example, is valid only because our dependent variable is in logs. And this is something that a lot of people were having problems on the previous homework. In this case, this coefficient cannot be interpreted as a percentage change. This is the value change on price, because price is measured at levels. So in this case was one additional bedroom costs you approximately $13,000 more in the price of the house.
Professor, how can you say
Yeah.
13,000? Like, why not $13?
Do you have your data open? If you look at the description of the data, it says that prices are measured in thousands of dollars. So even though it says 13 point something, the actual interpretation is 13 point something times 1,000, so it's $13,000 more. That's why it's always important to try to figure out what exactly the variables are measuring. All right?
Yes, guys.
Okay, so that is the Brown-Spagat test. Now, is this the only test to test for heteroscedasticity? No. The next more advanced, yes.
I have a question here, please. So can we consider that introducing log can solve for heteroscedasticity, or this is just here the case?
Okay, so logs might help you with heteroscedasticity, as in the case that you see here. It could be because of the reduction of the dispersion, or it could be because this functional form is better.
Oh, okay.
But that's not
So
always
it's not
going
a
to be
rule.
the case.
Okay.
It's not going to be always the case. And sometimes you cannot apply logs. You
Yeah,
simply
in
won't be
certain
able
cases.
to do that. Yeah. So
Okay.
in this case, it makes sense because prices, you usually want to talk about log of prices, not prices themselves, or log of wages, or log of GDP. But it might not be the case for other models. So applying logs sometimes helps, but it's not the solution.
Okay, thank you.
So the second test that we're going to see is the white test for heteroscedasticity. Now, this white test is very similar to the BP test in the sense of you're trying to run a model where your dependent variable is the predicted residuals square. But the difference is that you're including not only the original variables of the model, but you're also including interactions among the variables. So you should be including the squares of all the variables and the interactions of all the variables. So technically, you're adding the second order polynomials of all the variables in your model. This changes your null hypothesis because before we would only be testing for whether or not delta 1, delta 2, delta 3 are equal to 0. Now you have these 3 equal to 0 plus delta 4, 5, 6, all the way to 9 should also be equal to 0. You could still use not only an F statistic, but also an LM statistic if you prefer. So again, what's going to be the difference between the BP and the white test? That on the Braunschweigen test, you only included the variables that appear in your model. In the white test, you're including those variables plus the first order interaction plus the square terms of all those variables. So this has one advantage and one disadvantage compared to the Braunschweigen test. The advantage is going to be that the white test now would allow you to test for other functional forms other than the one that you start the model with to see if there is any presence of heteroscedasticity. What do I mean with that? It is possible that the errors do not vary respect to the linear function of x, but it might vary respect to the quadratic term of x. So it could have a quadratic form. Daniel, do you have a question?
Yeah. I'm just wondering, I understand the rationale of including, squared, squaring the explanatory variables. That does make sense. But I don't really understand the rationale for including interactions though, because I would assume that the purpose of having a regression in the first place is that you're understanding the relationship of one variable with the other while holding all others constant, right? So why would you want to include interactions, and isn't that kind of defeating the purpose?
To some extent, it's going to be important to add interactions in a general model because you believe that there are some interacting effects within variables. For example, if I would have included here, I could have also included something like number of bedrooms and the square of feet because there should be some interaction between these two variables. You cannot construct an excessive number of bedrooms keeping the number of square feet fixed, for example. There should be a penalty in doing that. And the same the other way around. It doesn't make sense to have an extremely large house with only one bedroom. So allowing for interactions allows you to account for some of these interactive effects of the controls. But that, of course, depends on the model that you're estimating. Something that is typical in labor economics, for instance, is not only to include age and education, but also account for age and education at the same time, for the interaction of both effects, because you believe that there could be perhaps some benefits of having more wisdom along with more education, for instance. Now, in this model, we don't care about the interpretation of the coefficients. The white test doesn't mind if there is absolutely no reason why you care about it using this particular interaction. The only thing that it cares about is that the more interactions that you add, the more non-linearities you're going to be testing. And that's the idea of the white test, is let's allow for more non-linearities to try to figure out if we can detect any kind of heteroscedasticity patterns. So why do we include interactions? Because we're trying to allow for more nonlinear factors or nonlinear effects between the explanatory variables and the square of the error, or if you prefer, the explanatory variables and the variance of the error.
Got it.
However, the problem of doing that, so the advantage is that you're going to capture more nonlinear characteristics of more nonlinear. You're going to capture or test for nonlinearity on the presence of heteroscedasticity. But the disadvantage is that you're including relatively a lot of coefficients to the extent that it might be difficult, if not impossible, to keep track of all of them. So I was making here a very small example that if you had 6 explanatory variables in your model, the official white test will require the estimation of at least 27 parameters. Well, when you have about 1,000 observations, not so much a problem, because you're not doing this manually, it's not much of a problem, but you can start thinking about it, that the more controls that I had, this parameter will increase almost exponentially. So is there another way to do this? To still account for non-linearities, but at the same time have a more parsimonious model? Yes, there is. And that is what is called the alternative white test for heteroscedasticity. What is the idea? The idea is that instead of adding quadratic terms and interactions of all the variables, so instead of adding not only the original variables plus the quadratic term plus the interactions, is to add the predicted value of the outcome plus the square of the predicted outcome. Now you think about it, this is going to be not exactly the same, but similar to adding the quadratic and the interaction terms of all the explanatory variables, with the advantage that instead of adding 27 parameters, as in the previous case, or 9 different parameters, as in this case, you're just adding 2 parameters. How does this change the outcome? Well, instead of testing for 6 parameters, for 9 parameters to be equal to 0, now you do it only on 2. And you can run this either using a Lagrange multiplier test or an F-test. I do this, for example, using, here it is. I'm using this for doing the same kind of a heteroscedasticity test for the model with log price of houses. And I find that, well, let me recap over here. So I run this model. I obtain my predicted price houses in logs. Again, I don't mind what exactly this means. I just need to get the number. I create the square of that parameter. I'm not re-estimating this because I'm just recycling what I had before from the previous model. I estimate this, and I can look into the chi statistic or the F statistic, and I find that I would also reject the null hypothesis of, or rather, I cannot reject the null hypothesis of homoscedasticity in the model. So we have learned 3 ways to test for heteroscedasticity. In all of these cases, the null hypothesis is that everything is fine, that the model has errors that are homoscedastic. You have the Brush-Pagan test that tells you just add the variables that you have in your original model. The white test that tells you add the original one plus the square parameters plus the interactions. Or the modified white test that tells you do not add the original variables, add the predicted values of y and y squared. Of course, here it doesn't mean that you can add other ones like cube, fourth, etc. What are the values of adding all of these? Probably very little, but it's another possibility. Sometimes this test will agree and give you exactly the same result. Some others, one might tell you that there is a problem of heteroscedasticity, while the other tells you that there is none. What do you do in those cases? It's really a lot about how do you interpret the results, which one you think is the stronger one, or you just keep adding more information to see if there is any agreement of all these tests. So after doing this, then you're going to have two scenarios. One that you reject null hypothesis and you have a problem of heteroscedasticity, and the other when you do not reject and you just continue as everything that was done until right now. You can do all your statistics, etc. Yes.
Could you go over the rationale of including the predicted variable, like the predicted value of y again? Like I don't really understand as to why would you want to do that? Like the modified white?
Yes. So the idea of this is to run a model to see if these will vary with respect to characteristics, correct? This is what we're really trying to test. Does the variance vary based on characteristics or based on control variables? So this is what we really want to want to figure out if it works or not, right? Now, if we're going to do this parametrically, meaning we want to add controls, we can either do this, sorry, we can either do this or this, and I think you are fine with doing any of these two, right? The
Yeah.
question is, why does it matter to you? Why is it important? What's the rationale of using a y hat? So what
Yes.
exactly y hat is?
So predicted value of y?
It's the predicted value, but it's just this, correct?
Okay.
It's the interaction of, it's the multiplication of the values times the estimated betas. So if I do this as a function of x, one of the possible functions of x that I could choose is just saying a function of x betas, which is a function of y hats.
Got it.
And I'm still falling within the same realm of talking about trying to figure out if the variance, the conditional variance, changes respect to characteristics. But instead of using many values, because here you could have a very large number of controls, I'm going to choose a single value that summarizes all of those. So instead of using x1, x2, x3, etc., I'm summarizing all of those into a single index that is the predicted value of y.
And the predicted value of y will include the interactions that are happening between the explanatory variables as well, right?
When you add y squared, yes, technically you're also including the interactions of x1, x2, and the interactions between these two.
Got it. Got it. And so,
Except that, yeah,
yeah, so the rationale of including y squared, the predicted value of y squared is just to see if there's any sort of quadratic relationship that might be there. So the modified white is just testing for another additional thing. It's testing if the relationship might be quadratic as well, right?
yes, I thought you do have the same with the standard white. Actually, the main difference and the main advantage of using the modified white is parsimony, because here you might have a very large number of original values plus the interactions, whereas here you only have two controls, y hat and y hat squared. So you're reducing a lot of the additional noise of adding more and more and more controls on the model. So it's really the main reason why we like the modified white is because it's much easier to apply and you don't have to worry about controlling for all those interactions. Even though the interactions are implicitly here.
Got it.
Does it make sense?
Yeah, it does. It does. Thank you.
You're welcome. All right. So again, say that you run your model, you run your heteroscedasticity test, and you find out that your model is heteroscedastic. What do you do about it? Well, what you're going to do about it depends on what you know about the problem. If you know what is the exact source of heteroscedasticity, you can apply what is known as the generalized least squares or weighted least squares and solve the problem before estimating the model itself. So option one is you know the problem, so you solve it. Option two is you do not know exactly the problem, but you have a very good educated guess, meaning you can kind of model heteroscedasticity, and after you model it, you can apply the feasible generalized least squares, which means you first come out with a model for heteroscedasticity, you obtain your predictions of the variances, and then you use those predictions to correct for heteroscedasticity in the model before you re-estimate it. So here is, you do not know, but you suspect. Finally, you know nothing because you do not know what could be the source of heteroscedasticity. and you don't care to make a model to figure out what could the source be. So what do you do in those cases? You know nothing. You simply say, I'm going to apply robust standard errors and go from there. So let's
Professor,
see what exactly, yeah.
with running GLS, there's probability of still having heteroscedastic problem.
If your guess is incorrect, yes. And that will happen both with generalized least squares as well as with feasible generalized least squares. If your guess is incorrect or your model is incorrect, it is possible that you still have a problem of heteroscedasticity. So at the end of the day, you might still have to rely on the last option, which is estimate robust standard errors. Nevertheless, doing this might help you to get a more efficient model, even if you end up doing robust standard errors at the end of the day. So let's start with the first method. The first method is a specific version of the generalized least squares called weighted least squares. So in this case, you assume that you know something about the source of or the nature of the heteroscedasticity in the model. For example, we can assume that the variance of the model, the conditional variance, is a function of some constant times something that makes the variance increase or decrease. So this means that I know, at least to a multiplicative constant, I know why we have a problem of heteroscedasticity. Now, this know why is going to be very hard. There are a few cases where you know exactly what's the source. And in the book, they mentioned the case of using aggregated data and get the means of aggregated data as a very well-known source of heteroscedasticity that can be corrected using this approach. So let's say, for example, that I know something about this function of h of x. So it could this I know I do not need to know exactly what the function is. I just need to know that there is a function of h of x. How can I use that information to improve my model? Well, one way to do that would be to transform my model from this to this model. The transformation assumes that you can, let's say, if you divide every single variable in the model, including the constant, because this is multiplied by 1, if I transform every single variable of the model by dividing it by the square root of the source of the variance, I can obtain a model that has an error that is now homoscedastic. So what exactly this means? What this means is that the weighted least squares, when you apply weighted least squares and you know exactly what the source of the heteroscedasticity of the model, you can transform your heteroscedastic model to make it homoscedastic. Because by construction, if you now look at what is the variance of the error, you're going to find out that the variance of this error star is homoscedastic by construction, because we are basically eliminating this component from the variation of the model. So let's say we have a model like this, where savings is a function of income. We might believe that this model is heteroscedastic, because the more income people have, the more likely is that their savings will be more erratic. So you're going to find that at higher level of income, a lot of people spend even more of their money. So they might have very little savings, sometimes even negative. Surprisingly, the more income people have, they tend to spend even more beyond their means. And some other people might actually decide to save even more what they would normally have, compared to the case where they have lower income. So we might suspect, for example, that the variance of the error is a function of income. So here, what I'm saying is that h of x is just income. So according to the weighted least square, or to this approach of the weighted least square, the transformation approach, it suggests that you should first transform every variable in your model, including the dependent and the constant variable, by dividing it, or you prefer multiplying it by 1 divided by the square root of h of x. So I should multiply every single variable here by the square root of income. So I can apply that to the model. Now, when you do this, you have to be very careful, because we also need to transform the constant. And because we are transforming the constant, this will no longer be a constant, will be something that varies, which also means that if you estimate this model, you have to estimate a model without a real constant, because our constant has now been transformed into something that varies. Now, if we apply OLS to this model, and if we assume that this is correct, this new error will be almost elastic. And assuming that the other assumptions of the OLS hold, this new estimator, or we estimate OLS on this model, is going to be not only unbiased and consistent, it's also going to be the best linear unbiased estimator compared to any other estimator there is. Because we are using the information not only on the source of, on the variation of the data, but also the why do you think you have an heteroscedastic error in your model. Now, there is another way to think about it rather than using transformed data. And this approach is probably the most appropriate because, again, people tend to forget to transform the constant and forget to drop the constant, which is using weighted least squares. Weighted least squares, because what we are going to try to do is to estimate a model where we weight each observation or each square residual by the inverse of the variance. What is the idea here, and why is it that this model will be more efficient than the OLS? Because we're going to give more weight to observations that have less variance and less weight to observations that have more variance. So if you think about, for example, in the graphic that I had at the beginning, it basically means that rather than depending on all these extreme values that are caused by the heteroscedastic model, I would only be concentrating on this segment, or at least putting much more weight on this segment of the distribution, because here things should be a little bit more stable, reducing the stability of this section of the data. Let's see where we're back. Also, for you to know, this weighted least squares is just a very special case, or very particular case of what is known as the generalized least squares. Generalized least squares, in fact, should address not only problems of heteroscedasticity, but also other kinds of problems like correlation or autocorrelation, etc. But when you do this in such a way that only care about heteroscedasticity, is called weighted least squares, which only considers or only addresses this particular problem. So let's see how would I apply this. Instead of using the model of savings as a function of income, I'm going to do something slightly different. And in this case, it's going to be a function of wealth. And try to figure out how wealth is determined by income, not really other characteristics, plus an error. And here I'm going to assume that everything else that is not measured on the data is just left out. So nothing that is on the error is going to affect income. So we're assuming exogeneity on the data, that there is no endogeneity, so we can forget about that problem. The only problem that we're concerned right now is about the problem of heteroscedasticity. Now let's assume that the source of the variance is this one, that sigma square, or that the variance conditional on x is a constant that you do not know but you don't care, times of h of x, and this h of x is just equal to income. Use this to estimate the models using weighted least squares. So how do we do this? The first option is going to be to do it using transformation, and just for you to know that transformation works. So again, for this, I'm going to use Rios and upload this data set, the 41K subs. Just to replicate the example that Woodbridge has in the book, you need to select that data with family size of equal to 1. So I'm just going to keep this data set. Here, Inc is the variable for income, net is for net wealth. And I'm going to make transformations of the data by just dividing all the explanatory variables, including the constant, by the square root of income. So I do this. And I estimate the model. Now, in this case, the constant has to be included, but I also have to tell Stata, do not include another constant to my model, because the original constant is there, it's just transformed. The other things that I'm including here is the original model, the one that will have heteroscedasticity, and the alternative way to doing weighted least squares, which is actually using weights in the model. And technically, this should be an AW, or analytical weights, equal to 1 over Inc. So these are my solutions. See that when we use the transformed data, it's exactly the same, or should be exactly the same as using weighted least squares. For the constant, the same. The other thing to consider is that the coefficients do not change much when I use the model without weights to one with weights. There is a small reduction, but that's expected because we are using different weights to analyze the data. But the overall conclusions from the model remains the same. In this case, what would be the interpretation? For each additional dollar of income that people have, their net wealth increases in about 82 cents. That's according to the original model. According to the transform model, for each additional dollar that people have, their net wealth income would increase in 78 cents or 79 cents. But if you look at the variances, the variance actually increased a little bit. And that's, as I mentioned before, that's very common. The variance of the model that doesn't consider heteroscedasticity is 0.061, whereas one that considers heteroscedasticity increases to 0.635, which is not much, which might suggest that either heteroscedasticity is not a big problem for this model, or that even considering heteroscedasticity has no strong implications on the statistical inference of the model. However, this is not necessarily the case for every single situation. There are other situations when you apply weighted least squares or transform least squares, that the results may lose significance or might gain significance compared to the original model. So that's not necessarily something to say whether or not you should or you should not apply this transformation. Also, I'm assuming that this model has heteroscedasticity because I already tested before. Before applying these results or this correction, you should be testing for whether or not it makes sense to solve for heteroscedasticity, if that is the case. Okay, so first approach, we know something, we correct directly by either transforming the data or waiting by the source of the heteroscedasticity. But what if I have no idea what's the source of heteroscedasticity? What would I do? So what if I do not know the functional form? I basically have no idea what functional form this should be. It could be any of these ones, just income, income square, income cube. It could be that there is another variable that I should be considering, multiplied by gender, something. I have no idea. So what do we do? When you do not know what the functional form exactly is, but you still want to apply something similar to feasible generalized least squares, is that you can come up with a solution by making some predictions of what this h of x should be. Because at the end of the day, this is what we care about, what h of x is. So how do we come up with something like this? Well, we could start by analyzing a model or by stating what exactly the model implies. What we're trying to say is that the variance should be a function of a constant times h of x. And because I want this h of x to be strictly positive, because variances cannot be negative, I could assume that this h of x is just an exponential function of x's and deltas. I know that this will always be positive. So I can start by saying, let's substitute this by what I know. I know that I cannot use the variance directly, but I can use the square residuals. And this square residual is going to be equal to a constant variance times this prediction of my h of x times a multiplicative error that I don't care about either. But I do not know how to estimate a model for this. So what do? We apply logs. With that, we transform our dependent variable now. And we make this exponential function to a linear function that I can estimate now. I can use OLS to estimate this model. So I substitute the unobserved errors with the errors that I do observe that I get from the model. I estimate my coefficients, and then I make an estimation or a good guess of what that h of x, I should really call it h of x hat is. Now you might recall, and I would like somebody to say, wait, didn't we learn in the past that this is not the best way to predict of h of x, right? Because we are forgetting about this error, and we should be including this error on the prediction. Well, the reality is that it is true, this might be important, but we don't care because we just care about estimating the variance up to a constant. So if we forget about including the error from this model, it's fine. We still use this. Instead of this, you could also have included this as a caveat or as additional piece of information. And now that I have this h of x, I can apply weighted least squares, meaning I can re-estimate my original model. Regression of y as a function of x1, x2, x3. Using this h of x hat as my weighted variable, or my weighting variable. So let's see. And for this, I'm going to give you one of the shortcuts that you can do in Stata. So let's start with this. So we're going to use the dataset smoke in this case. Here, try to use smoke. And we're going to start with this model, which is cigarettes is a function of income. Let me get out of here. Okay, so we start with this model. We assume that everything is homocelastic. We should first should estimate or test for whether or not there is heteroscedasticity in the model. You already know the steps, but because I know the steps, I don't need to go with all of them. I can just test it directly. You can use this only for the brush pattern test if you want to verify that what you will be doing is correct. In empirical terms, you can either do this manually or do this using the stat command. I mean, you should only do an stat command because that already does it for you. But just as a note, I would prefer if for the homework you do this manually because you need to learn how exactly it's working on the background. But you can verify your results using this. Anyways, so I estimate the model where the idea was to figure out if the number of cigarettes that people smoke is a function of the log of income, log of prices, education, age, and these restaurant prohibitions to smoking. In general, would say that the more income people have, the more likely they're going to smoke more. But the higher the prices, the less likely that they're going to smoke. More educated people smoke less. I'm uncertain about the impact on age, but most likely the older they are, the more likely to smoke an additional cigarette, but that seems to decline a little bit with age. However, because of the prohibitions in the restaurants, the amount of cigarettes that people smoke has declined drastically. In all of these cases, both income and prices seem to have no statistical significance because each one of them have p-values that are lower than 2 or lower than the critical value, or if you prefer, the p-values are above 0.05, so they are not statistically significant. However, the question is this because really that's going on, or because our standard errors are incorrectly estimated? So one solution, first test for heteroscedasticity. According to this, I do find that there is a problem of heteroscedasticity because I will be rejecting the null hypothesis of constant variance. So what I can do next is, well, account for heteroscedasticity by applying feasible generalized least squares. So how do I do that? Well, I estimate the model. Just make sure that that's the last model that was in memory. I predict the residuals. For residuals, I could have just written residuals or just the shortcut for res. Now these residuals should have a mean 0 and variance of whatever it is. You can verify that they are the correct residuals because the correlation between residuals and all the explanatory variables should be exactly 0. Because by construction, that's what it should happen. I'm going to create the square of the log of the residuals to estimate my model. Then estimate the model. Now, this is not necessarily a model to test for heteroscedasticity, but you can already see that the log of the residuals do vary respect to income, respect to age, education, etc. So this is another way to look at that. In fact, there is a problem of heteroscedasticity. Now, why do we choose to use residuals square and not log of the residuals for the model? I do not know. That really I do not know. But in reality, the rules say you should use residuals square to do that test. Okay, so we estimate the model in logs. We made the predictions. And we exponentiated those predictions to have a prediction for the conditional variance of the error. So the last step would be to estimate the model weighted by my by 1 divided by the predicted conditional variance. Now, this new model should have either a lower level of degree of problem of heteroscedasticity or no heteroscedasticity at all. And we can compare the models of 1 and 2. Let's see if I compare that here. Let me compare them here. So this two file. So let me compare them here. There's the store in 1. So here are my two models. You can see now with the stars to mark if something is significant or not. And what has changed? Because we are applying a reweighted approach of the method, the coefficients are going to change, but you should expect them not to change by much. When they change a lot, that usually implies that there is a problem on some of the other assumptions. But in this case, except for the local prices of, except for the coefficient of local prices, and perhaps a little bit of age, the coefficients haven't really changed much. So we can assume that the model has no other problems except for the potential problem of heteroscedasticity. After I control for heteroscedasticity, I find, for example, that even though originally the elasticity between, or semi-elasticity of smoking cigarettes as a function of income was non-significant, after I control for heteroscedasticity using the weighted least squares, I do find that the elasticity is actually a little bit larger and statistically significant. With respect to prices, I find something that is also expected. It's still non-significant, but it's a little bit stronger if you look at the t-square, the t-statistic of local prices. This was before using the reweighted approach. The t-statistic is almost 0. With this estimated approach, it's a little bit larger, although still quite small. It does have the expected sign that higher prices reduces the chances of people to smoke, but is not statistically significant. For everything else, the results remain considerably consistent to the original one, with the standard errors that are much smaller than the previous case. However, more than looking at the standard errors, it might make more sense to look at the t-statistics, because the t-statistics provide you a better sense of the standardized coefficients, standardized in the sense of the coefficient divided by the standard error, to see if there were any improvements on the efficiency of the coefficients, on how precisely the coefficients are estimated. And in all the situations, the t-statistics have increased, which suggests that this modeling is more efficient than this one. And again, it's more efficient because we are now using some of the information of the fact that the original model was heteroscedastic. You want to repeat all of this? Again, you can just copy most of the code that I have here, except for the comments. Everything that is in blue with a hashtag, you want to just copy paste it in a do file in Stata. You should be using a star, because for Stata, stars are used for comments. I hear somebody had a comment.
Can you send us like a do file at the end of this or something like that too, or is that?
I'm not keeping a track of the do file, but everything that I'm typing is on the slides. I'm just copy pasting from there. So the discussion was, now the model is statistically significant, other coefficients are more precisely estimated, although with some changes on the magnitude of the coefficients, but not really in the qualitative value of those coefficients. So everything in the story remained the same. Now here is something that I believe, Aria, you asked before, in the sense of, what if our correction is wrong because the model is wrong, or we are not using the right functional forms to estimate to estimate the conditional variance. So what happens in the model? Well, if our heteroscedastic problem is misspecified, weighted least squares are still consistent in the sense of, remember that heteroscedasticity has no impact on the consistency or the unbiased properties of the coefficients, assuming that everything else holds. The only thing that is different is that if you believe that your model is misspecified, even though you're correcting for heteroscedasticity, you should still try to further correct for the errors, applying robust standard errors, which we're going to talk next. Now, one way to figure out if these assumptions 1 to 4 were holding or not is to check how different are the estimated coefficients. If the estimated coefficients are about the same neighborhood, like it was the case comparing this cigarette model, most of the coefficients are in the same neighborhood except perhaps for the log of income. If they are in the same neighborhood, then everything is fine. Your model, even if the model is misspecified, everything else remains consistent, even though they might no longer be biased, and that's a little bit because of how much weight you're providing to some variables respect the others. However, if the coefficients between OLS and WLS, or weighted least squares, are very different, it usually means that either assumption 1 is wrong or assumption 4 is wrong, meaning that either you're missing some nonlinearities on the model, or that the model itself there are some factors that are endogenous, and that's why when you apply weighted least squares, your coefficients change drastically. So in that situation, you really have to go back and figure out if the model specification was correct, or if there are any other problems with endogeneity in your explanatory variables. Nevertheless, if you think you have a very strong heteroscedasticity problem, and most of the time that's going to be more because of the theoretical properties of the model than the test itself, is going to be mostly or most of the time better to use a wrong form of heteroscedasticity correction approach, because you still get a little bit of gains in terms of estimation of the efficiency of the coefficients. Nevertheless, again, you can always rely on robust standard errors just to be on the safe side of estimations and statistical inference. So what are robust standard errors? That is what if I do know nothing about the source of the standard errors, and I don't really want to guess because I'm afraid of guessing incorrectly, and I don't want to mess with that. So when that happens, it is still possible to get good estimations for the standard errors, but one has to be careful because all the other formulas that we have learned so far for the estimation of these standard errors of the betas are going to be wrong. So we need to change how they are estimated. The only caveat of doing this is that the standard errors, the robust standard errors, are not valid where your samples are small. At least the one that Stata estimates using robust is not appropriate when you have small samples. You really need large samples to do that. So why are the estimations not correct? And where exactly these robust standard errors come from? Okay, so a little bit of math here just as a refresher. Recall that in general, the general functional form of the beta coefficients on the estimated betas is that they follow something like this, where the estimated beta is just the true beta plus some weighted errors, and these errors are the errors in the population, not the errors of the sample. So if this is the true estimation of or rather the approximations of the coefficients, and I want to estimate the variance of the betas, I can just apply the variance function to all of these, and I would obtain something like this. Here, I'm assuming that these W's are exogenous. That's why I don't need to apply them, apply the variance on them. They can be taken out of the parentheses, and I have a function that looks more or less like this, where the variance of the betas is nothing else than the weighted sum of the variances of the errors. Now, under homoscedasticity, you can simplify this formula because the variance of the errors is a constant. So if this is a constant, I can substitute that here. And this formula becomes something like this, where the variance of the betas is equal to the variance of the error times some weighted factor. Now, you are more familiar with matrix algebra. You probably have seen this in the sense of the variance of the betas is equal to the sigma square the errors times x transpose x inverse. This term here is basically this. Under heteroscedasticity, however, this cannot be done because you cannot say that this is a constant for everyone. So what do? The best approach would be to say that this variance is substituted by just the errors of the square. This is going to be the best approach to assume of what is the variance of each individual has. This transforms my model, or the estimation of the variances, to keep it in this form. Now, this makes the math a little bit more difficult because you cannot just take this out and simplify your formula. You have to estimate this for every single observation. You have to estimate the weights, multiply by the square of the errors, aggregate it all back to obtain the variances of the beta coefficients. And what's the idea behind this? The idea is to assume that each observation has its own variance. So in order to calculate the variance of the coefficients, I have to weight each observation's variance in order to obtain an accurate overall variance of my coefficients. Now, how do I actually apply this? Well, normally you would have to apply it by hand, but the Stata has many options. You have robust, PCE robust, plus other approaches that are better than just doing this. Now, most software, again, robust, most statistical software already have procedures that deal with all the background estimations of the standard errors. So the estimation of this mathematical formula that is much more complicated is already dealt by Stata. You don't need to do anything. You just need to tell them what you need for it to provide you the robust standard errors explicitly. So something that people usually wonder is, why is it that if that's the best way to approach to deal with heteroscedasticity, why is it that that's not the standard? Why do we still need to learn the results under homoscedasticity? Now, this I take because of what Woodbridge says on the book. There are three main reasons why you want to start with the standard under the assumption of homoscedasticity. First of all, tradition. We all start in the same way. We start by assuming that the model has no problems. And under the idea conditions is that you can start learning all the properties of the coefficients and the properties of the estimations and properties of the methodologies. The second reason is that at least this approach to standard errors is valid only in large samples. And remember, not more than perhaps 20 years ago, the idea of large samples was a little bit more constrained. So usually you would deal with much smaller samples, especially when a lot of this theory came out. Nowadays, we don't really have to worry about large samples unless you're running your own data. So the second reason why robust standard errors is not really valid. In fact, if you look at discussions papers, all of them usually suggest or usually tells you that they are already reporting for robust standard errors. But there is a third reason. Sometimes these robust standard errors can be less efficient than homostochastic errors. So if you have a model that is almost homoscedastic, you could still just report homoscedastic errors. However, if you apply robust standard errors, you might be providing standard errors that are a little bit larger than it should. So you are really being less efficient by trying to use more information in the model. In this case, it's one of the few situations where this becomes contradictory. By trying to apply more information in the model, you become less efficient because you're wasting resources to some extent in applying robust standard errors when homoscedastic standard errors should be just fine. And there is a fourth reason that has become quite contingent in the last, at least over the last couple of years. People keep bringing it back, which is there are many approaches or many options for what you would call robust standard errors. If you are of a user of R, for example, R provides you with, by default, it will provide you with the asymptotic standard errors, the one that we start with. But it also provides you with options to report the H0, H1, H2, and H3 standard errors, robust standard errors. Stata by default uses H1, which basically means you use this formula and you adjust for degrees of freedom. But a lot of recent research has suggested that rather than using HC1, you should use HC2 or HC3 as your default because they are better when you have small samples. Now, is that really relevant? Probably not for most of what you have to do. But if you think it's important, you can always request it and just go from there. The other thing is that these HC2 and HC3 are only, at least as far as I know, only important for OLS. When you go to something else, MLE, what's the other, GMM, not sure for Bayes. I don't think it's actually relevant for Bayes. When you use MLE and GMM, the idea of a HC2 and HC3 is not really relevant. So there is no equivalent for those. I'm not going to tell you what HC2 and HC3 are, but if somebody is really interested in, we can talk about it and I will tell you exactly what they mean. In any case, sometimes might be a good idea to at least observe or report the asymptotic standard errors and the standard robust standard errors. Now, once you correct for these standard errors using robust, most statistics will provide you with correct P statistics and correct F statistics. However, you cannot estimate this F statistic as we have done before, meaning, and let me show you this, I think it does give me something. So for example, in this model over here, what I want you to look at here is, this is the F statistic that you know how to estimate. We have done that, we can create it by hand, etc. Is basically equal to looking at the changes of the square of the residuals divided by the number of restrictions divided by the number of degrees of freedom. This is the F statistic when you apply robust standard errors that is completely different from this one, which means you cannot estimate this using the formulas that we have learned before. You have to use it, or you have to estimate it using this other formula, which is a little bit more complicated. It basically says that you need to always estimate it using the variance covariance of your coefficients, including the restrictions of the model, and divided by the degrees of freedom. So I'm not going to ask you this to be done manually. At best, I'm going to ask you to use test and see how the results change from using homoscedastic errors or under heteroscedastic errors. And this is what I tell you here, that you don't really need to learn how to apply this, because the command test will already do this for you. Alternatively, if you want to check the book, you can also apply the LM test that is robust to the presence of heteroscedasticity. So let's see how things change when you apply the different robust standard errors. So in this case, I'm going to use the, let me increase this so I see better. So I'm going to use the dataset WAGE 1. And I'm going to estimate the model using homoscedastic standard errors, the standard robust standard errors, the one that is taught in most of the books, and the two other ones just for the fun of looking how exactly you can request them in the state. And we are going to report all of them just looking at the standard errors. So first thing to notice, first of all, this correction of standard errors only makes a difference for the standard errors themselves. The coefficients will be the same. There is nothing that is done to the coefficients. So a lot of the questions usually come as in, I'm trying to address heteroscedasticity, I'm applying robust standard errors, but my coefficients do not change. Is there a problem? No, because the only times when the coefficients will change is if you're applying weighted least squares. This is not that. This is corrections that go directly on how the errors are estimated, not how the coefficients are estimated. So because of that, in all of these cases, the coefficients are exactly the same in all the models. The only thing that changes are the standard errors of those coefficients. Going, for example, from, in this case, from the normal standard errors, from homoscedastic standard errors, from the robust, in most of these scenarios, the standard errors increase, which is expected. As I showed you at the beginning, standard errors tend to understate the true variation of the coefficients in the presence of heteroscedasticity, and this is exactly what this is showing you. Because of this, the coefficients are increasing, but that might not be the case in every single situation. Looking in the case of education, or at least in the case of experience, the variance of the coefficient actually declines a little bit, and the same for experience squared. So most of the time you're going to see these increases in the coefficients, but sometimes they might decline. Now, when we go from the robust standard errors to the HC2 and HC3, those coefficients actually increase, and this tends to be much more consistent, that the variances become even larger when you go from robust to robust number 2 or robust number 3. And the reason for that is that these other approaches to estimate the standard errors try to be a little bit more conservative and try to create a standard error that is, in general, a little bit larger, to be less likely to fall into a type 2 error of just rejecting the null when the null is true. What about the impact on the F statistic?
Just, sorry.
Yeah.
ESTST, do I need to load that command or something? It doesn't, it's this command not recognized.
You need to install, that's a good one. To get that, you need to install ssc install store. Oh, it's not a store, it's stout, not a store, it's stout. You need to install this command to have that est option.
The stout.
Yes. Once you have a stout, you can do the stab and the store to store the coefficients into an object. This
Does
is what I'm
that
doing
stay
here.
resident, or you have to do that every time you're going to run it?
Only the first time. So you have to install it only one time. Unless there are updates, you only need to do it once. After that,
Oh.
it will always remain in your computer.
Yeah. I don't want to complicate things, but and then so the clear command clears just the present. It seems like sometimes I have to clear and then I have to reload everything, and it's a little bit vague when and what gets cleared and when and what stays resident.
Okay. So this is more like a general question. What I'm doing here, and let me erase again. Clear all. This clear over here just means clear the data set that you have in memory and load this new one. Everything else, all the other programs should stay in memory. Now, these are where I'm going to store this regression. I'm going to store in M1, M2, M3, and they may or may not disappear. So that is true. Just typing clear might keep this in memory. So it's better to just re-estimate it. And that's why I always recommend write a do file, so you don't have to worry about all of that and just run the do file all together to replicate everything. But for now, Jonathan.
Oh, I'm struggling conceptually to understand how the coefficients all remain the same, but the errors can be like plus or minus, I guess.
Because
between homoscedasticity and
so in all of the cases,
Rubus,
the betas are still estimated as X transpose X, X transpose Y. So it doesn't matter how you estimate the standard errors, the betas are still estimated like this. So that's why they do not change. The only thing that changes is how do you estimate the variance of the betas. That depends on how you're going to aggregate these errors. If you aggregate them, let me discard. Erase. Okay, so the difference really is how do you aggregate those errors? If you aggregate them like this, you have the homoscedastic errors, because the only thing that you're doing is taking the errors away and then getting some aggregation of the excess. Whereas when you do robust standard errors, you're aggregating it like this. So it's a slightly different way to aggregate those errors. So in one case, it's variance of beta hat equal to sum of this squared divided by n minus k times sum. This is version 1. And this is version 2. So these are two different aggregations, and that's why you have differences in how the standard errors will look like. But the betas are still X transpose X, X transpose Y. That's why they do not change at all. You're just changing how these errors are treated to estimate the variances. Now, this HC2, HC0, HC1, let me write it over here. HC0 basically estimates the errors with no degrees of freedom, just divided by n. It's not exactly like this, but conceptually it's just divided by n. HC1 does the same, but divides it by n minus k. So you account for degrees of freedom on how many parameters are estimated. HC2 doesn't divide by the degrees of freedom, but estimates the errors in a different way. It estimates the leave one out error, which is beyond what we should cover here. But it basically means what would have been the error if I estimate the model with all other observations except this one, and I predict and I make a forecast of the error based on everything else but this observation. And that becomes this. And HC3 is something like this. And I don't remember what exact formula for this, but it basically inputs even more weight on the fact that you don't want to have the model error, you want to have the out of sample error. So again, a lot of complications on the math, just to say this version and this version, try to account for the fact that using the errors hat might be incorrect because they are part of the model itself. You want to do it with information that it's outside of the model because that becomes better in terms of the statistical properties of the standard errors. But again, for all of these cases, betas are still estimated as X transpose X, X transpose Y. That's why the betas do not change at all. The only thing that changes are those standard errors.
Okay, I'll think about it a little bit more. I'm struggling with the like conceptual what this means for the model overall. But
All right.
go ahead.
We can also talk about it in more detail. Sometimes it has to go with all the math on why exactly this is happening.
Yeah.
But I don't want to spend too much time on that right now.
Yeah.
All right. Okie dokie. So where were we? What about the F statistics? Again, using different estimations of the standard errors of the. This is the under homogeneity. These are the robust HC2 and HC3. Your F statistics are going to change slightly. And the larger changes are going to come usually if the problem of heteroscedasticity was much stronger. In this particular model, it seems that heteroscedasticity, even though it's present, is not as strong, and that's why the conclusions do not really change much by just applying the robust standard errors. Now, one more thing before we go into a break. And let's go to our old friend, the linear probability model. One of the problems of the linear probability model, linear probability model had three major problems. Number one is that it could give you predictions that are impossible because it will predict that something has a probability beyond 1 or below 0. So it's less likely that impossible, most likely than perfect certainty. The second problem was that unless you apply more flexible functional forms, it tends to say that the impact is always constant across the distribution. So the impact of an additional child on the probability of working is the same as the second child or the third child or the fourth child, etc. And that's why you have the first problem. Now, the third problem of the linear probability model is that the linear probability model on itself is heteroscedastic. And if the linear probability model is heteroscedastic, the t statistics are wrong, the f statistics are wrong, and you cannot really do a statistical inference when you're running a linear probability model. However, now we have learned that there are at least two ways to deal with heteroscedasticity. One, we could apply weighted least squares. How do we do that? First, for a linear probability model, the source of heteroscedasticity is exactly equal to this, because this is the source of heteroscedasticity for a binomial model. So because I have this, or I can estimate this, I can re-estimate the model using weighted least squares. Simple. What is the problem in these cases? If y hat is larger to 1 or less than 0, this formula will not work, because it will give you, it will predict an age that is different or that is smaller than 0, and then you won't be able to do much with that data. You have to drop it, and you don't want to drop the data. The other option, of course, is that if you use linear probability model, you can just apply robust standard errors and you'll be done. So I believe that's one of the questions that I have on the next homework. That tell me why is it that you cannot apply this in that model and estimate robust standard errors, so you can tell me whether or not your conclusions change when you were assuming homoscedastic errors or when you correct for the possible heteroscedasticity of the errors. Okay, let's take a 5-minute break, and we will be back for the second part, in where we're going to cover some additional problems, or we're going to try to tackle some of the additional issues regarding to some of the other assumptions in the model. And what I mean assumptions in the model, assumptions on the ordinary least squares. All right, I'll be back.
Professor, I think you're mute.
Yes, I was just working on something before we came back, but this was more for Jonathan. I'm going to explain it in a little bit. But thank you. Yes, list close enough. I think I need to. All right. So this is for what we're talking, Jonathan, in terms of the what makes the difference between the robust standard errors and the normal standard errors. So the example I'm doing here is on MATA. MATA, it's you have worked with R before. It's similar to R in the sense of you can use matrices to work with some data much quickly than you would do in standard data ADU. And I'm doing this just to show some of the math behind of what Stata does to create the different standard errors. So for this, I'm using the data set. Well, you can upload it from here, the Oaxaca data set. And I'm going to use only data with information with wages. And I do that so I don't have to deal with missing data in this section. And I could have included information on missing data, but for now I'm dropping it off. My dependent variables is wages, and my independent variables are education, experience, tenure, and a constant. So this is the constant, just forms of ones. All right. So first thing first, how to estimate the beta coefficients? Normally, I would say just use regress, LA wage tenure, education, experience, etc. However, what is really going on in the background is that we're applying the formula beta is equal to x transpose x inverse times x transpose y. Now, in mathematical terms, for something the computer can understand is x transpose x is equal to the cross product of x with x. X transpose y is the cross product of x and y. And instead of the inverse like this, I'm saying let's use the inverse function. So with this, I can estimate the beta coefficient. And let me stop there just to see if it actually matches what the regression would do. So it matches exactly the same. So this is what Stata is doing on the background. Well, actually, there's a little bit more of a numerically robust approach to calculate the same coefficients. Now, how do we estimate the variances? For the variances, we first need the estimations of the errors. And the estimations of the errors is exactly the same as before. It's y, what we observe, minus the predicted y. So this x, this y hat is equal to the x transpose p. Now, the asymptotic standard error is just to estimate the sum of the error square divided by n minus k, minus 1 if you want to include the constant. N is the number of rows, k is the number of columns for how many variables, including the constant that you have. And this correlation, actually, I could probably do either the correlation, or I could have done the sum of the square residuals. I should say be exactly the same. Just a different way, which should be a little bit faster. to get the square residuals. So if we just follow the formulas, under not asymptotic, but under homoscedastic, under homoscedasticity, the standard error is nothing else but the sigma squared times the inverse of x transpose x. So let me stop here. And this variance covariance matrix is what the what regression will provide me as it is. So it's under homoscedasticity. The only thing that is being done to estimate the standard errors is just multiply the variance of the errors times the sum of the W's, which in this case is just the inverse of the cross product of x times x. So this formula here is the equivalent to DCD is equal to sigma squared times x transpose x minus 1.
So, Professor, what you're doing is just proving what the starter is doing, like you're giving
Mata.
background of
Basically, yes.
yeah.
And it's just to show you what is the difference between and why is it that the only the standard errors change when you apply robust standard errors and not the coefficients. Now, for robust standard errors, this becomes a little bit more complicated, and I needed to check my math for estimation of the variances. The formula for the variances is far more complicated than before. Is all of this. Under homoscedasticity, this guy over here became I times sigma squared. That's why I was able to put this out and then eliminate one of these with the inverse. So we became relatively simple. This is what we do with under homoscedasticity. Under heteroscedasticity, you can't. You have to estimate the variance for each individual, multiply by x, and obtain the variance, the robust standard errors. Now, this element over here can also as x transpose x as this. So I'm basically making a separation of these once I include the I break down that variance formula and multiplication for the x transpose x. So you should be writing something like this, and that's what I have on my formulas here. Where are you? Yeah. And that's exactly what I have here. I have that first I need to create that new variable that multiplies the x's times the errors. And then I can make the cross product of that times the inverse of x transpose x times the inverse of x transpose x. So this is the formula that runs on the background when you run robust standard errors. But these errors are still the same ones as I started with because they depend exactly on the same beta coefficients. So if I look at this, I obtain these standard errors that are close to the ones that would obtain using theta, and the difference is that this one are also correct for the degrees of freedom. These ones do not. This is divided by n. This is divided by n minus k. So actually, I think I could do. These are technically speaking, these are the HZ0. The HC1 would be this times rows x divided by rows x minus rows x. So let me change the name of this. This is what the status reports, which are the HC1 that corrects for standard errors, for the degrees of freedom, and the formulas that I think that also on Woodbridge do not correct for degrees of freedom, and that's the equivalent to the HC0, which is only reported in R, if I remember correctly. So this is the source of where all these different variance covariance, or the different ways to estimate the standard errors come from. As I mentioned, there is also the HC2 and HC3, but they require the estimation of something called what is this? The little h hat. It's a little component that allows you to estimate the leave one out error without really re-estimating the whole model. So I'm not going to reproduce it here. I have that in some of my notes in some other do file. But it's just another way to estimate this number here. So if you adjust that, but everything else is the same. You readjust that, you calculate you recalculate this multiplication of the variance times degrees of freedom or re-estimation of this component, because this remains the same. This varies a little bit, and you can estimate from the robust to the DCE HC2 or the HCT HC3. But all of them, again, are just manipulations of the error, not manipulations of the beta.
So
and that's why.
So basically, like before, we were spending time taking some data set, figuring out some model based on that data set, and RSE maybe takes that model and revises how we're actually calculating errors, while like weighted least squares or what the other feasible GLS adjust how we're going to determine those betas.
Exactly, and that's why a lot of the confusion comes, because people expect that by adjusting for the standard errors, you should also adjust the betas. But that only happens when you use weighted least squares or FGLS, because that reweights everything.
Because then we're changing how we form the model in the first place, because our data set isn't assumed to be hetero or homoscedastic.
Yeah, so even in those cases, though, the assumption is that the original model is still correct, and that's why you expect that even after adjusting for using FGLS or weighted least squares or whatever strategy, you expect the coefficients to be similar, or at least in the same neighborhood.
Yeah.
But the coefficients change a lot, then you say, okay, there is another problem for my model.
Okay.
When you apply robust standard errors, you assume the model is fine, the specification is fine, so the coefficients do not need to change. The only thing that require adjustment are the standard errors.
Okay. Thank you.
That's it. You're welcome. And I will try to save this, or let me save this, so if you want to explore a little bit of matter, you can do that on your own, at your own time. So let me. But don't worry, I will not ask you to do matter, since that's a little bit more complicated and it took me a while to learn it myself. All right, so where were we? More on the specification and data issues. Okay, so we just discussed a lot of the problems that are associated with assumption number 5 regarding to homoscedasticity. Now we're going to backtrack to discuss problems with assumption number 1, the linearity of the model. So one of the core assumptions of the linear model is that whatever you choose as your model, that functional form is correct. And the functional form that we have kept talking about is just, let's assume that the model is linear, even though we usually say linear in coefficients. We implicitly always go to use a linear in variables as well. So we never say, most of the models that we have seen is, let's say, price as a function of number of bedrooms. We don't say price as a function of bedrooms, bedrooms square, bedrooms cube, the log of bedrooms, etc. We usually tend to go only with one parameter. So implicitly, we are saying, let's assume that the function is linear in all the terms possible and go from there. However, that simplification might be an oversimplification and might not provide you the best model when you do want to do something other than estimating marginal effects for the average person. In other words, if you want to say something for somebody else, for the extremes, for the ones who is very well educated or is farther away from the city or has a lot of experience, for that person, using a linear model might not be the best approach because the prediction might be very far off from what his income is in general. So the question is, how can we know what's the best functional approach or what's the best functional form for my model? What I used to say, for instance, is how do we know that instead of using for a data that goes like this, that instead of using a linear model, how do I know that it's in fact, shouldn't this be something more like quadratic term? Quadratic term. What if in fact is, I don't know, kind of exponential or cubic or something? We do not know a priori, except for a little bit of guidance based on theory. You will not really know what should be the right functional forms before applying a model. You can guess, but getting the exact one is going to be difficult. And it's even more difficult when you have to consider also interactions. Now, was it Denial who said, do we care about interactions if we want to keep some of the factors constant? Sometimes we might care about interactions because interactions might give you literally what is the interactive impact of two factors that shouldn't be considered separate. So I cannot, something that a person, there is a paper that discusses a lot about this idea of the ceteris paribus and says things like, you cannot really measure the impact of experience keeping age fixed or keeping tenure fixed, because the more experience that you get, you have to get more tenure and you have to get older. So in those situations, you cannot keep them fixed. So how do you apply that into the model? One of the ways to do that and to explicitly allow for that interaction is to use interactions on the model itself. But again, a priori, some of these interactions might not be as obvious, and you cannot just overfit the model and have all the possible interactions because you end up with other types of problems as well. What we have to cover now is that there are other ways that we can use to actually figure out if we are missing something of our model or if we can improve in terms of the functional form. Yeah, so the first way to figure out if you need to do an interaction or a higher, what's this, a higher polynomial term could be to just add that parameter to your model. Let's say you start with is equal to 0, alpha 1x, alpha 2 x2 square, or x1 square, is to see if this parameter is statistically significant or not. Is it significant? If it is not, well, you can take it out and just continue with the model, or if it is, just keep it in the model. But again, this could be a very good way to test one by one if a variable needs to be included in the model or not, but it might not be the best approach to figure out if you are missing all the possible quadratic terms or cubic terms of interaction that you need in your model. In other words, sometimes there are so many interactions that you cannot really test for all of them. So if you want to really test whether or not the functional form of your model is adequate, you can do something called the reset test, which allows you to provide a general test to see if there is something missing in your model, with the caveat that this might give you an idea of what is missing, but not exactly what is missing. In other words, it might tell you you need to add something else, but it won't tell you what you need to add to the model to make it better. So what's the nature of the reset test? It's actually going to be very similar to the white test that we saw before. So the idea is to start with a model that you have with all of these terms. You're saying y is a function of a linear set of factors of x1, x2, x3, etc. Next, you create predictions of the model as it originally was, and you add the square and the cube terms, or square, cube, fourth if you prefer, and test whether or not these parameters are significant to the model. Implicitly, what you're doing is saying, what if I include square parameters of any or all of the parameters that I have originally in my model? Or what if I include not only the square, but also the cube or third degree interactions of all the variables in the model? So clearly, this is saying, what if my model is misspecified because I'm missing some cubic or quadratic terms? Can this test tell me, well, we are going to test whether or not these terms are missing in my model. So the test would be, are these parameters statistically significant? Unfortunately, well, on the one hand, doing this test is straightforward. You just see whether these are significant. But if they are significant, you're still at a loss because you just know that something is missing, but not what is missing. So let me try to do that in this example of housing prices. So I start with the data set of housing prices. I model this using, well, my model is a linear model of prices as a function of the lot size, the square feet, and the number of bedrooms in the house. I use the prediction to obtain the predicted value of the houses, and I calculate the square and the cube parameters, and re-estimate the model including the square and the cube. Question, why is it that not adding this just as it is, the level of prices? Because I'm only adding the quadratic term and the cubic one. Why wouldn't I be adding this as well? Anybody has any idea?
Because it'll be
Yes.
perfectly collinear with the dependent variable.
With all the other independent variables, exactly. So this is perfectly collinear with all the x's, and it will be dropped. So that's why we do not include it. Okay, so I add the square and the cube parameters. I test for whether or not they are statistically significant, and according to my test, I reject the null hypothesis. Therefore, my model is misspecified. There is something that is missing. There is something that I could add to improve on the fitness of the model. The question is, what am I missing? I have no idea. I just know that there is something else that I could add to the model. So a different way of seeing whether or not, or what would happen if I choose a different model specification. So instead of that model, now I use one where my dependent is log of prices as a function of log of the lot size, log of the square feet, and bedrooms. Remember that this model was heteroscedastic. It's not only heteroscedastic, but it's misspecified. Now you know that this model is homoscedastic. The question is it misspecified? Well, I go to the same procedure, predict the log of prices, calculate the square and the cube. I include them in the model, and I do a joint test and see if they are statistically significant or not. And what do I find? According to this, I cannot reject the null hypothesis that they are are jointly equal to 0, which means there is more chances that this model is not misspecified. So everything should be fine. You can proceed with without worrying much about missing some non-linearities in the model. At least that's what this is telling you. Again, unfortunately, the reset test will tell you something is missing, as he was telling you here, not what is missing, what you should be including. Something else that you might be considering when thinking about misspecification is how to test when you have two alternative models that have the same explanatory variable, but have different, that are explaining the same dependent variable, but have different explanatory variables. In this case, model 1 and model 2 are called not nested models. Now here, the idea of nested models is where a model, let's say I create a model number 3, is nesting this other two, because I can make this disappear and then it will look like model 1, or I can make the other two disappear and it would look like model 2. So I can make it look like the other two models by making restrictions of the coefficients. In this case, model 1 and model 2 are nested within model 3, but model 1 and 2 are not nested. So the question is, which one of these two models is the best to explain something? There are going to be two ways to do that. Number one, you can create a nested model and then test for whether or not model 1 or model 2 are appropriate by just testing whether beta 1 and beta 2 are equal to 0, or if beta 3 or beta 4 are equal to 0. And that way you can say, is model 1 appropriate or model 2 appropriate? Unfortunately, if you do that, you might end up saying, well, model 2 is inappropriate and model 1 is inappropriate, or the other way around, model 2 and model 1 are both appropriate. So this is one of the caveats of model misspecification with not nested models, in which case you can also apply, when something like that happens and you cannot reject one model from the other, you can always use an R-squared to figure out which model is the best in terms of the explanatory power. Now, even though this way of doing the nested models is one of the approaches to do a test for two not nested models, you can also apply what is known as the Davidson-McKinnon test. That is just a shortcut for what I did before. The shortcut is, rather than creating a third model that nested all of them, I simply create predicted values from my first and second model and see if those predicted values add anything to the other model. For example, in my first model, the predicted values of the second model provide any additional information. If this is equal to 0, so they do not provide any additional information, then the first model should be correct, or at least is the one that I would prefer over the second. The same one over here. Does the first model have enough information that improves over the second one? If I would say no, so I cannot reject the null hypothesis, then I would probably prefer model 2. Otherwise, I might prefer model 1. So what happens if both models are rejected? So it seems that the other one is better, or in other words, that delta 1, or rather lambda 1 and lambda 2 are statistically different from 0. Usually suggests that you need to have even a better model, probably combining the information of both. What if you cannot reject either, so both models are equally good, is when I say you can probably use the adjusted R-squared to see which model might become better, or which one has the most explanatory power. Now, this is another point that is very important for analyzing data, and that is not really covered in the assumptions of the model, although it's implicit. When you collect the data, any kind of information, you have the underlying assumption that all the information that you have collected has good quality information. For example, if you go and I ask you to collect information on grades and age of people in BART, you expect that, and I'm assuming that you're going to choose people as random, so that's not a problem of sampling. I would expect that, well, what would you expect in terms of what kind of information they're going to give you if you ask these two questions? What is your age and what is your grade? Are they going to provide you with adequate information, with reliable information, or they are more inclined to lie? What do you think? And let's add one more variable. So you're asking their grades, their age, and their gender. What do you think is going to happen when you ask these two questions? Are they more likely to lie on all of these or not? Most likely, well, people cannot lie about gender unless it's going to be very difficult to distinguish. So you can verify it because you are the ones interviewing. So the variable of gender will have very little, if any, measurement error. You find somebody and you write it as male or female, they are going to be most likely like that on the data, and that's going to be reliable to whatever they actually are. In terms of age, probably there's going to be a little bit of a measurement error for different reasons. Number one, some people might be reluctant to tell you their actual age, but probably most people will give you the exact age that they have. I mean, there is less, what would be the word? Shame, perhaps, in telling you age, considering that everybody would be perhaps between 18 to 25 years old in college. So that chances of getting a lot of measurement error there would be very minimal. But there would be some measurement error depending on how you're defining age. You define age as number of years of life. Chances of measurement error very small. You define age as the number of years, months, days, and hours. Chance of a measurement error probably a little bit larger. Still random if people are just rounding their age, but there's still going to be something. What about their grades? That's a question that we usually say it has a lot of sensitivity, the same as income. Thus, people might really tells you, or that information, or that variable might have a lot of measurement error because people are less likely to tell you what their exact grade, especially if it's lower than average or higher than average. So they might tell you actually that they have a better grade than they actually do, unless you provide some other types of coverage in terms of how the information is being collected. Basically, if they have to answer anonymously, most likely they will tell you their true grade. But if he's not anonymous, less likely that they will tell you unless they have very good grades. Well, that note aside, the problem here is that most of the data that you collect will most likely be affected by measurement errors, meaning whatever you're trying to measure is not going to be what is actually measured on the survey. There is going to be some error between what you're trying to capture and what is actually answered. One of the assumptions of the linear regression model that we tend to not really mention that much is that we expect that all the data that we're collecting is measurement error free. So if somebody in the dataset says they have 5 years of education, you expect them to actually have 5 years of education. If somebody says that they have an IQ of 200, you expect that they have an IQ of 200 and not something else. Nevertheless, there are some theories, or there is some way to treat this when there is, because we know that there is going to be some measurement error, there are some ways to treat about it or treat this information, or at least know what to expect when this happens. And the problems that we're going to cover right now is for a very specific type of measurement error, which is called the classical measurement error. Now, classical measurement error is an error, that has an expected value of 0. So in average, people tell you the truth. And that this is also equal to 0, meaning that error is completely uncorrelated to the true values. So if you collect information for everybody who's 25 years of age, some of them might tell you they are 25, 26, 27. Some of them they are going to tell you that they are 24, 23, 22. But in average, they're going to be saying that they are 25. And whatever reason why they give you higher or lower age is going to be completely uncorrelated to their actual age. This is what we call classical measurement error. Now, when you have classical measurement error, and that measurement error occurs on your dependent variable on the left-hand side, nothing happens on your statistics. You can still run regressions. You can still get unbiased estimates. The only thing that is affected is that when you have large measurement errors, your sigmas or the betas are going to increase. Why are they going to increase? Because all that measurement error ends up going to the error of the model itself. So what are the consequences of measurement error on the dependent variable? Number one, the estimates that you're going to have are going to be less reliable. Are going to be less precise because the variance is going to be higher. But other than that, your OLS is still unbiased, it's still going to be consistent. You collect enough information, this additional impact of the measurement error will be minimized in your model. The problem, however, is when the measurement error happens on your explanatory variables. So if for some reason people tend to lie on how old they are, you're going to have a bigger impact on the estimations of the betas, because this measurement error kind of creates an endogeneity on the model. One way to look at this is that why is it that having measurement errors will create an impact on the betas? Let's see if I have this. So consider something like this. You have a beta, a true beta, that is related, not exactly the same, but is related to the correlation of y and x. However, there is also the beta 0, I'm not going to call it 0, that's 0, that is going to be the correlation of the dependent variable and this measure. This is the nature of your measurement error in this model. Now, if this is a true measurement error that is independent of the dependent variables and the independent variables, this should be equal to 0. So when you put together the true data and the error, the beta that you're going to estimate is going to be a sort of weighted average between the true beta and 0. So then what happens? When you have classical measurement error on the dependent variable, you're going to have this in my next slide. You're going to have something that is called attenuation bias, which means because of the additional noise that you have on your dependent variable, you're less likely to actually identify the relationship between the dependent and the independent variables, and the coefficient that you're estimating will be most likely to be closer to 0. So in this case, the OLS is going to be biased and inconsistent, and it doesn't matter how much information you have, the inconsistency will always remain there as long as you have measurement error, because the inconsistency is coming from a sort of introduced endogeneity in the model. Now, a good way to look at this is if we do a very small experiment. So what I did here is start with the data set on wage 1, and I created a new variable that has a perfectly exogenous measurement error with mean 0 and a standard deviation 2.1. So education is my true variable, and education error is my variable with a measurement error. So I can estimate this model and this other model, and we can try to compare what happens with the estimated coefficients. I'll do the same, even though I don't include it here. I do the same for adding some additional error on my dependent variable by just adding some other noise of similar magnitude. This magnitude is given by the standard error or log of wages itself. So if you do some log of wages, you can just create this log wage error equal to the original log wage plus the random normal times the standard error that you obtain from the summary. So what happens? This is my original model. This is the one with measurement error on education. My coefficient gets attenuated towards 0, because now this variable is less capable of identifying the causal relationship between wages and education, because a lot of this new variable is basically noise. So we are attenuating the coefficient by adding more noise to the estimation. What about yes?
Professor, why can you repeat it once again? Why did you multiply it by 2.8?
This?
Yeah.
I was just trying to create a new variable that has a classical measurement error. So the original variable is education. Now classical measurement error is when there is some additional error, there's an additional factor that is added to the true variable, but is completely uncorrelated. So the correlation between x and this extra factor is equal to 0. That's exactly what I'm doing here. I'm getting my original data, and I'm creating another one that is the original one plus some noise. So this variable education error is my variable of education that includes a measurement error, a very strong measurement error. That's why I was adding that over here. And that was just to show you what happens when I estimate this model versus this model over here. And what happens? Look at the coefficients. This remains basically the same. Well, there's a little bit of a decline. This remains basically the same. But the estimation of education now becomes half as large. And it's half as large because the size of the measurement error that I'm included here is just as much as the variation of the original data. Now, this other model, model 3, was just to show what happens when the measurement error is added not to the dependent variable, sorry, not to the independent variable, but to the dependent variable, to wages. So look at the coefficients. The coefficients are very similar. This one is much more different because it was already estimated with very little precision. But this one, what is with much more precision, is still about the same, in the same neighborhood. But look at the coefficient, the standard errors. The standard error increased almost double. Over here, increasing almost 50%. So this just reflects the characteristic that I just mentioned before. Number one, when the measurement error happens on the dependent variable, the coefficients should be about the same, but the standard errors are going to be much larger because you're losing precision on the estimations of the coefficients, even though you're still capturing the same causal effect, the same direction of the effects. When the measurement error happens on the dependent variable, on the independent variable, in this case education, you're introducing endogeneity in the model, and your coefficients are going to be biased towards 0. That's why this coefficient in this case goes from 0.09 to 0.04. In other words, in the example I was giving you, if I ask people their age and they constantly give me an incorrect age, and that incorrect age is all over the place, even though in average is going to be the correct one, most likely my estimation of the standard of the coefficients is going to be much smaller than what it should. So what's the message that you should get from this? That if you believe the data that you have is measured with error, most likely the coefficients that you're getting are smaller than the true coefficients. If you believe that the error is on the dependent variable, your betas will be fine, but the standard errors are going to be much larger than the true standard errors. Okay, so let's go over the last assumption that some people will already answer through the homeworks. That is the assumption of random sampling. So we mentioned a couple of times that the main reason why we want a random sample for your estimation of the model is because you want to say something about the population. And if your sample is not random, then you cannot say anything about the population. That is mostly true, and mostly true in the sense of the best case scenario is when your sample is truly random, so you can really say something about the population as a whole. A lot of the time, however, you are forced by one reason or another to collect information of a subsample or analyze data for a subsample of the population. For instance, you could decide to do your analysis for working population, for men versus women. So you are creating not a random sample, but you're selecting a sample of men, women, mothers, etc. And in those situations, you can still apply OLS, and you can still have models that represent the population, but only under very strict assumptions. Alternatively, you could have these kind of subsamples. You just have to change the question or the nature of the question. What do I mean with that? If you work with a sample of only mothers, it's not going to be a random sample of the population, but it could be a random sample of the population of mothers, and all of your results are going to be applicable for mothers only. And when you do that, your results might not be necessarily affected because your analysis will be focused on a different subsample of the population. Now, this works if and only if when you do the sampling or this non-random sampling is based on exogenous factors. And what I'm going to define exogenous factors is that the random sampling is defined either by variables that enter your model as independent variables, or that you have an exogenous sampling by design. Exogenous sample based on design is going to be, for example, if I want to analyze, I don't know, the labor market profiles of mothers, my design is to work only for mothers, therefore it's an exogenous sample. The other one is random sample based on dependent variables. Could be if I constrain my data based on gender, because I decide to separate the analysis for men and women, I can still do that, and it's still going to be a non-random sample, but based on exogenous factors. In other words, this idea of exogenous sampling happens when the samples are chosen based on independent variables or based on exogenous decisions. And when you do that, even though it might seem that you're violating assumption number 2 of OLS, you're not completely going against it because your sample is still random of a smaller subsample of the population. And the main reason why this is not going to create a problem is because your regression conditions on that variable, and therefore the nature of the non-random sample is already included when you're estimating the model. The problem happens if you ignore the nature of that random sampling. What do I mean with that? Let's go to the example of doing the analysis for men versus women. If you know that you're estimating that you're using women for your data, and you estimate a model for women, you can say something about what happens with women outside of your data. You can explain, based on my modeling, I can say what is the wage profiles for women everywhere else in the nation, etc. However, what if for some reason you do not know that your sample was only made for women and you were thinking that the sample was for everybody? Because you do not know the nature of the random sample or the random sampling, you cannot make any conclusions about the population because your conclusions are going to be incorrect. That means that whenever you try to do any sampling and you do not know the reason for that sampling, you're going to have models that are going to be biased and inconsistent. And one way to get this kind of inconsistency on the sampling is when you do sampling based on your dependent variable. And we're going to see that in a second. The other thing to consider here, even if you have a model that is based on a subsample, if the model is correctly specified, you can still make extrapolations and say something about the population. So let's say that you want to say something about the US population in terms of their wage profiles, but for some reason you have data only for people between 25 to 40 years old. If your model is correctly specified, it might be possible for you to say something for people beyond 40 years old because you're making predictions of what their wages could be. Your modeling is bad, you're going to be far off from the truth, but if the model is correctly specified, you might be able to say something correctly for people even though they were not part of your original sample. And for this, I think it's better to do it with a visual example. So imagine this scenario when I have two subsamples of a population. The blue line and the red line, orange line, the only difference between these two is that one is I'm running a regression for individuals with X that are below 0, and the other one is for individuals with X above 0. Now, if I model this, I can probably reasonably say things about people that are within this sample. My model is misspecified, so I can still probably say something about these individuals. The problem would be that if my model is misspecified, I cannot say something about these individuals using this data because I'm going to be very far off. And that happens both ways. However, if my model is correctly specified, and in this case, I know exactly that I should be using a quadratic model, I can use data from this side to make predictions of what happens on the other side, and I'm not going to be too far off from reality. So I can still make extrapolations of what happens beyond of what my sample would allow me to. And that happens again both ways. So the lesson is, if your sample is correctly specified, then you can make extrapolations for the population. But if the sample is misspecified, then probably you can only talk about your subsample. That's why if you read some papers that are collected with a very specific sample, the language that they are going to use is usually our conclusions are valid internally for the data that we have and for people that look like the data that we're using. Some others, however, are going to say, and we can do a back of the envelope transformation or a back of the envelope estimation and extrapolate for other populations under the caveats that it might be false if their characteristics are too different from ours. But we believe in our model, so we can make those extrapolations, even though they are far off from my model. Now, what if you happen to do selection based on unknowns? And I already explained you one of the options for that. What if you, for some reason, you have data only for women, but you're trying to do the analysis for the whole population? Your estimations are going to be off most of the cases because the information of where the data is coming from is unknown for you. Another way to think about these kind of non-random selections is when we introduce what is known as endogenous sampling. And endogenous sampling happens when the data is constrained based on the dependent variable. For example, if you select data based on age and you do the model using age as your explanatory variable, then you're probably going to be fine because your sampling is exogenous, based on something that you can control in the model. However, if what you're doing is selecting your sample based on income and you're trying to explain income, it's like you're trying to do sampling based on the error, which is an unknown. And if you do that, your results, your estimations are going to be far off. A visual example with a caveat, and I'm going to correct this before I re-upload it on Brightspace. Consider this scenario. When I'm doing random sampling based on X only, and in both cases I'm using the correct model specification, so I don't have problems with that. It doesn't matter if I use the information for these guys. I can extrapolate for the other guys, for the ones with X bigger than 0, even though I'm using data for X less than 0, because I will be using a sample that is exogenously selected based on the dependent variable. Now here, this is the graph I need to correct. The idea was to run two models based on sampling that depends on Y. One will be running based on this data and the other one based on this data. And both models are giving us incorrect results, even though the model specification is correct. It's a linear model. Using this data over here is giving me something that is too high with a much flatter coefficient, and the same if I would happen to use data on the lower side. The slope is much lower, and the predictions were far low for what they should. In those cases, well, here the lesson is very simple. If you think that for some reason your sample was selected based on the outcome, then it's almost certain that your results are not going to be consistent nor unbiased. And one of the examples that are typically used in these cases is, for example, if you try to analyze wages in the market. Because who are the ones who are going to be in the market? The ones who probably have wages that are above their shadow wage. So who have a potential to earnings high enough that they decided to get into the job market. But that means that some of these wages is part of the error, and the sample that you're having is a function of an unknown. So all of the models that we have talked about wages are technically biased because most likely there is some sort of endogenous sampling because wages, because the reason why we have individuals in the labor market is because they have high enough wages to participate in the job market or to have found a job that they were interested in, and we are analyzing wages only for them. So very likely that our results in all of the previous examples were biased. How can we solve for that? We can solve for that. There are other strategies that allow us to account for some of this kind of endogenous sampling, but we're going to see that in the future. For now, that's all. Yes, Jonathan.
So this like has to be the most prevalent thing in data science. Like every data set has some sort of assumptions around it. So when we're like getting data sets, I know right now you're just like giving us data sets, but is there just a generic part where people describe the data, or maybe even in Stata, is there like some data description that says like these are all Americans, these are all women, kind of stuff?
That's the part. I thought it's not as common to be done in economics. At least there was a small discussion on Twitter that came out some time ago. In economics, people tend to drill you. You put too much emphasis on the description of the data. So because everybody knows that if you're using CPS, it has to be for the US, well collected, etc. It's less likely that they're going to require you to describe the data itself. In other sciences, social sciences, sociology, political science, etc., they are most likely to ask you to provide that information, because with that information, you can know whether or not it makes sense to find the results that you have in your data.
Yeah.
Now, that is in terms of the exogenous sampling. In my papers, I'll always, in most of the papers that I use to do wage analysis, I always try to emphasize that I'm using people between 25 to 64 years old, because I'm focused on the core of the labor force. I try to use people who are already graduated, so there is less room for them to acquire more education, so they already make all the decisions. If I want to estimate their returns to education, for example. But I always put that little caveat of there could be some endogeneity problem, because if I'm using people who are in the market, for men it's not so much of a problem. Usually the idea is that the reason why men go to the job market is at random. But every time that we try to use women in that kind of framework, most papers refer to, you use women, you have to account for the fact that not all women participate in the job market, and the ones who are participating are quote unquote different from the ones who are not. So they have very specific motivations to do so. And because we do not know what motivations those are, you might be falling within this problem of endogenous sampling, and you have to do something else about it. So in academic papers, most of the time, the solution that we do is saying, if something like this happens, at least you acknowledge that there could be some problems, but you let it go. Because not all methodologies allow you to control for this kind of endogenous sampling. But at least you should say, I believe there could be some endogenous sampling that could affect my coefficients in X, Y, or Z direction. And again, there is only one methodology that I am aware of that allows you to do that, which is the Herman selection model, that allows you to some extent to deal with things like this. When you have, when you're using the sample of only positive size, for instance. And I'm going to try to get to that. I thought we're probably going to cover that towards the end of the year. Any other questions? All right. So if there are no more questions, homework due next week, just like this time or like last time, is due for Friday at 5. This time there won't be an extended deadline, because I want to send you the solutions to the homework either by Friday at the same time or Saturday at the latest, so you can use it to study for your midterm. And the midterm is going to be next. When did we say? The Thursday, the 20th? Yeah, Thursday 20th in class for all the period of the class. And where are you? Oh, I think he's not here anymore. If somebody else is taking the class fully online, I'm going to contact you to address how we're going to do that. So it's fair to the people who are going to be taking the class in person, or the exam in person. Other than that, see you next week. I'll be there, so I hope to see you there and finally meet you. And
See
if
you.
not,
Thank you.
thank you and enjoy the weekend. Take care, guys.
Thanks.
And don't forget, you have any questions, better you contact me before, because this homework has much more stata requirement than the last one. So just as a warning. All right, guys. Take care.
Thank
Yeah.
you.
Maybe we could do a planned office hours or something. I'm doing all right with it, by the way, but
Just send me an email whenever you want to do that. I mean, right now my schedule is relatively flexible unless something happens with, well, if I'm here, meaning here at home and